Welcome to the second video in my series on proving the Twin Primes Conjecture. In the first video, we learned about factor channels such as the ones you see here on the screen. In this video, we extend the factor channel concept to the twin primes in the form of motif tables. The motif tables allow us to represent the logic behind the distribution of the twin primes that leads to the precise approximation of the twins' distribution that we saw at the start of the first video. Let me walk you through the process by which I transformed factor channels into motif tables. First, we rotate the factor channels 90 degrees. In Theorem 1a in the first video, we labeled the number line with A through F. Here we do it again. You will recall, we discovered that the numbers labeled with B, D, E, and F cannot be prime. I have shaded the numbers labeled D, E, and F. We'll remove them, but we'll keep the numbers labeled with B for reference. Since the D, E, and F numbers can never be prime, they can never form prime twins, so we won't be needing them in the table. Now we're going to put each multiple of 6, the B numbers, together with the numbers preceding them, the A numbers, and the numbers following them, the C numbers, all on the same row. And since we have limited our table to the numbers on either side of multiples of 6, we no longer need the 2-factor channel or the 3-factor channel. So we'll delete them and start with the 5-factor channel, which we will widen. In fact, we will widen every factor channel as follows. Now let's align the 3 number columns with the factor channels. We have labeled these numbers with A, B, and C, but let's change the B to a small letter K. These are multiples of 6. I call the numbers that precede the multiples of 6 alpha complements and label them with an alpha symbol. Similarly, I call the numbers that follow multiples of 6 beta complements and label them with the beta symbol. I call the entire row with the alpha complement, beta complement, and K a K row. You will recall that in the first video we looked at Theorem 1a, which explained why every prime larger than 4 is a multiple of 6 plus or minus 1. We also covered Theorem 1c, which noted that for every pair of twin primes larger than 4, the first twin equals a multiple of 6 less 1, and the second twin equals the same multiple of 6 plus 1. So you can see that these two theorems make motif tables possible. The K rows constitute all of the numbers that can become twins. The blockages establish which of those rows, however, do not contain twins, and therefore apply to the entire row. We treat the row as a single unit. Now you may be wondering why it's called a motif table. To explain that, we need to make a few more changes to the table. First, we must add a column of numbers to the 5-factor channel. To obtain the number in the first row, we divide the alpha complement by the factor, which in this case is 5, and place the remainder in the factor channel. So 6947 divided by 5 gives 1389 with a remainder of 2, and 6953 divided by 5 gives 1390 with a remainder of 3. We do this for every row. Next we add a similar column of numbers for the beta complements. So 6949 divided by 5 gives 1389 with a remainder of 4, and so forth. Now if you look closely at these two columns of numbers within the 5-factor channel, you will notice that they consist of repeating patterns. Here I've surrounded the repetitions with red boxes to highlight them. I call these repeating patterns motifs. In music, a motif is a pattern of notes that repeats within a given musical composition. The idea is that if there is indeed a music of the primes, as described by Marcus du Sautoy's book of the same title, then these repeating patterns are motifs within that music. So the motif for the 5-factor channel is 0213243041, and that pattern repeats over and over forever. Now you will notice that every time a row in a motif includes a remainder of 0, that row is marked as a blockage. This of course is because if the remainder after we divide a complement by 5 is 0, then 5 is a factor of the complement. It therefore blocks that K row from containing a pair of twins. Using modular arithmetic, also called clock logic, we can predict the motif patterns. Definition 9a. The alpha motif pattern for the Q-factor channel is the sequence alpha sub j mod q, where j varies from 1 to q. The alpha sub j sequence is here, and the alpha motif pattern for the 11-factor channel is here. We can prove that the motif patterns constitute what I call unique hour clocks, as this theorem demonstrates. Definition 9g. A Q-hour clock is the set of integers from 0 to q-1, where q is a member of the set of natural numbers greater than 1. Definition 9h. Individual members of a Q-hour clock are referred to as the hours of the clock. Definition 9i. A unique hour clock is a sequence of integers whose members cycle through all of the hours of a given Q-hour clock exactly once before beginning a new cycle. Theorem 2a. No more than one zero residue per Q-factor channel per K row. The word residue simply refers to the result of, say, 7 mod 5. So it's the remainder after we divide the 7 by 5, which in this case is 2. This theorem holds because the alpha complements and beta complements are separated by 2. The lowest Q-factor 5 is larger than 2. Clearly, if one of the complements is a multiple of 5, the other can't also be a multiple of 5, since they are separated by less than 5. The same, of course, is true for all Q-factors. Theorem 2b. 2 blockages per motif pattern. For every complete motif pattern within a factor channel, there will be exactly 2 blockages, that is, 2 rows that contain a 0 residue, a blockage for the alpha complement on one row, and a blockage for the beta complement on a different row. Because the alpha motif patterns and the beta motif patterns have every integer from 0 to q-1 exactly once, both have one and only one 0 residue. And because the 2 0 residues cannot be on the same row, they must be on 2 different rows. Therefore, there will be exactly 2 blockages per complete motif pattern, as required. As we shall see, this last conclusion makes it possible for us to calculate the number of partial twin pairs with 100% accuracy. Here is a theorem presenting the formula that we will use to count what I call partial twin pairs. Definition 12. A partial twin pair exists when a given K-row is not blocked by any of the factor channels listed. Definition 13. A free row is a K-row that contains a partial twin pair, that is, does not contain any blockages. Definition 18. We say that factor channels are equalized if their motif boxes align on the bottom row of the table. In this table, for example, the 5-factor channel and the 7-factor channel are equalized on row j equals 35. Theorem 2f. Partial twins formula. When m minus 2 consecutive factor channels are equalized at the jth K-row, the number of partial twin pairs up through that K-row is given by equation 2d. Bar theta sub m equals j times q sub 3 minus 2, the quantity over q sub 3, times up through times q sub m minus 2, the quantity over q sub m, where q sub m is the highest principal factor whose channel has been equalized. Let's see how the formula calculates the number of free rows. Here I have highlighted every free row with transparent green. As you can see, there are 15 free rows, or partial twin pairs. We can calculate the number of free rows for just the 5-factor channel as follows. Var theta sub 3 equals j, which is 35, times 3/5. The 5 cancels with the 35, leaving 7 times 3 equals 21 free rows. Now we include the term for the 7-factor channel. Var theta sub 4 then equals 21 times 5/7. The 7 cancels with the 21, leaving 3 times 5 equals 15 free rows total. This gives us the correct number of free rows. The lowest number at which factor channels can be equalized is the product of the factors. Here we have the first 4 factor channels aligned at the bottom on row j equal 5005. The column preceding each factor channel contains a 1 in the cell if the k row is a free row up through that factor channel. At the bottom, each of these columns is summed. These sums then are the brute force counts for the number of free rows for each of the 4 factor channels. The calculations for the number of free rows are as follows. As you can see, they match the counts exactly. This will work for any number of factor channels so long as they are equalized at the bottom. Why is this so significant? It's because what we are discussing is the distribution of prime numbers, which is normally shrouded in mystery. Their distribution is thought to be, above all, unpredictable. Yet here we have discovered an island of predictability in that ocean of unpredictability. Clearly, the motif table concept goes a long way towards setting forth the logic behind the distribution of prime twins. Note that the count the formula yields is exact. It's not an estimate or approximation. It is the count. Consequently, the formula used is combinatoric. Combinatorics deals with formulas for counting things. Hence, the reason I have titled the article containing the proof, A Combinatoric Approach to the Twin Primes Conjecture. The motif table you see here goes up to row j equals 60. This table includes the first 5 principal factors, not including 2 and 3, up to q sub 7 equals 17. The principal factors are just the set of prime numbers. I call them principal factors or basal primes and represent them with q sub m. This is to distinguish them from the prime twins, which I represent with p sub n. Definition 22. A basal prime is a prime that is a principal factor of numbers up to a given prime square. If, for example, we take as our basal primes q sub 4 equals 7 and q sub 5 equals 11, then we can say that between q sub 4 squared equals 49 and q sub 5 squared equals 121, there are 4 pairs of twin primes. P sub 17 equals 59 and P sub 18 equals 61 are the first pair, along with the 3 others shown. Part of what I'm saying in these videos is that earlier primes, the basal primes, play a role mediated through their squares in the distribution of later primes, those that form twins further out on the number line. We are used to the idea that primes play a role in the formation of composites, but the idea that they play a role in the formation of other primes is new and revolutionary. In any event, the next principal factor for the motif table is q sub 8 equals 19. The square of 19 is 361, which is the beta complement on row j equals 60 of the table. Since 361 is the square of 19, we must add the 19 factor channel to the table if we wish to calculate the number of twins up to and including 361. Here is the table with the 19 factor channel added. Note the blockage in the 19 factor channel for row 60. If we did not include the 19 factor channel, the calculation would mistakenly count row 60 as having a pair of twins. Prior to row 60, the 19 factor channel did not need to be included, since every blockage by the 19 factor channel prior to the square of 19 is nullified by a smaller factor. Definition 15. A nullification of a blockage occurs when a smaller factor blocks the same k row from being a twin prime as a larger factor. We say that the blockage by the smaller factor nullifies the blockage by the larger factor. Here we see an example of an earlier factor nullifying a later factor. The 5-factor channel blocks the same k row that the 19-factor channel blocks. Thus it nullifies the 19-factor channel's blockage. You will notice that when a blockage is nullified, the table represents it with a lighter shade of gray as compared to when it is a blockage for a principal factor. In the next video, we extend our formula from partial prime twins to actual prime twins to produce the precise approximation shown here. I'll see you there. Be sure to subscribe and press the bell so you will be notified when the next video in the series becomes available.